Go live for a
Okay.
moment.
It's okay now.
Wait, let me just see. I'm not sure. Uh-huh. All right, it's live. Let me just announce the speaker. Today, Misha will give a talk about common infinity categories, its construction and properties. Thank you so much. Misha, please take it away.
Thank you. I go on to talk about common infinity categories. So we start with the motivation. So the motivation of this this construction is motivated by the model independence and the different and also by constructions of colimits and limits and adjunctions. So you can express such notions as colimits and adjunctions via common infinity category. So in infinity cosmos, and also common infinity categories are preserved by functors of infinity cosmoi. So this notion is invariant under weak equivalences, and this is sort of in invariant language. I suppose it is convenient to describe different stuff by means of this notion. Okay. So we can encode limits, colimits, adjunctions via common infinity categories, and these notions will be preserved by infinity. Once again, by weak equivalence of infinity cosmoi. Okay, and now I recall some motivational things about quasi-categorial stuff about smattering factors. So consider some quasi-category Q, and its homotopy category has elements of Q as its objects, homotopy classes of one simplices of Q as its arrows, so we have the following picture here, and we know about composition relation. So if you have a diagram like this, it means that GF is weaknessed by H or equivalent to H in homotopy category of quasi-category. So we discussed these things last time. So let J be one category. So J is an ordinary category. We know that in general this we have this problem. So you have no isomorphism between homotopy coherent diagrams of shape G And oh, sorry, this is a typo. So homotopy coherent. Okay. I mean that this is a homotopy. So you know the problem with that homotopical limits don't coincide with the ordinary limits, and we have no isomorphism like this. But there is a comparison functor between homotopy category of diagrams of shape J and homotopy coherent diagram. Homotopy coherent diagrams. So this is simple. This is defined simply by transposition. So you have an evaluation map from this category to this is ordinary evaluation map, and after that you apply the homotopy functor H and transpose this, and you get this natural comparison functor. In particular, you can put J to be walking arrow or north of walking arrow. This is a correct notion of this object. So this is just delta of 1, and you will have the canonical functor. We discussed this canonical functor comparison later last time, and this functor is smattering, meaning that it is surjective on objects, full and conservative. That is, it reflects invertibility of morphisms, but this functor is not necessarily injective or nor faithful. So we know about this thing. We discussed it when we talk about quasi categories. So once again, I recall that recall the notion of smattering functor. So a functor between infinity categories. Infinity categories is smattering if and only if it has the right lifting property with respect to the set of functors. So this is equivalent definition. So it corresponds to the first condition. So surjectivity on objects. It means that the solution of corresponding lifting problems problem corresponds to the fullness, and the last arrow corresponds to conservative property. Okay. And the following lemma about mushroom fibers. It tells us about that each fiber of a mushroom functor is a non-empty connected group weight. So suppose that you have a mushroom functor, say F, and consider consider a fiber. So form this pullback diagram and consider this fiber. Then it turns out that it will be non-empty connected group weight. Another lemma said that this comparison functor is a smattering. So for any J1 category which is free on reflective directed graph. And also, if P is a isofibration, meaning that there is a solution of this problem, Lifson problem, the canonical comparison functor is also Smaltra. So these lemmas motivate further consideration, and the next example for any tower of isofibrations between quasi-categories. So suppose that you have a tower like this. These fancy arrows means that they are all isofibrations. Then the comparison functor is Smorthran, and also for any cospan between quasi-categories, you can form the following pullback. The pullback like this is very important because this object is so-called comma category, and we will see the general definition of this object. But it turns out that in this setting, this functor is Smalthran. So this lemma is also like motivation for further development of this stuff. Okay, so Smalthran functors are important for us. They express weak universal properties of arrow, pullbacks, commas, constructions, and in the homotopy 2 category of any infinity cosmos. So we can use these Smalthran functors to express some weak universal properties. And one can derive them, and they are in some sense equivalent. So if we have Smalthran functors, then we have weak universal properties. It's sort of paradigm or some setting in which we will work. So now the first important example of common infinity category is an infinity category of arrows. So consider some element element of infinity category. And it corresponds to the vertices of the underlying quasi-category. And now we can introduce the following definition. If A is an infinity category, then infinity category of arrows, or just this symbol, AA2, where 2 means as usual the walking arrow, north of walking arrow, and together with the isofibration like this. And this isofibration is induced by the inclusion of boundary of one simplex to the delta 1. And these two arrows, P1 and P2, we can consider some two arrow between them. So and these two arrow will be is called generic arrow. So the following lemma states that for any infinity category A, the infinity category of arrows, which we have already introduced, comes equipped with a canonical two cell. So you have a canonical two cell like this. Why it's true? So know that we have an isomorphism like this. So we in the series of first seminars, we talked about we wanted to have this isomorphism like this, and we in this case we by this reason we define two like n of 2 or north of working arrow. So from definitions we have the following isomorphism, and we can take the identity morphism on A2. So we can put X to be A2, and we can take an identity morphism on A2, and this morphism maps to the to some element of this guy. So we have a one simplex in this functor category. So, and this one simplex will represent desired to cell K. So it's an easy application of unit dilemma. Okay. And what about these two cell K? We wanted to show that the boundary of these two cell is just the desired one. So we should prove that this two cell is between P0 and P1. So to show this, consider the following diagram. So we have an original isomorphism, and consider the following obvious inclusion: 1 + 1 into the working arrow, and this inclusion induces the following vertical arrows. And of course, you should and obviously you have these isomorphisms, and from the commutativity of this square, we get that the boundaries, the boundary of these two cells is as desired. So is you see that you have a codomain and domain maps, and these P1 and P0, and by commutativity, of course, you'll obtain that codomain is okay. That's easy. Okay, and by the unit dilemma again, you have you can apply the homotopy functor, but after this after the application, you won't have an isomorphism or even natural equivalence of categories, but anyway you have some map, and this map has the weak universal property of the some weak universal property. So consider the generic arrow, and this generic arrow has a weak universal property in the homotopy 2 category, and this property is described by the following three operations. So the first one is one cell induction. So suppose that you have a two cell alpha between two one morphisms S and T. Then you can you can describe this this diagram as this one. So you will have a morphism from X to A2. So such that alpha equals the Whiskeran of between alpha and this K, this two cell K. The next property is about two cell induction. So given two functors, A and A prime from X to A2, and natural transformations tau 1 and tau 0. So you have a picture like this. Then in this case, there exists natural transformation tau from A to A prime, such that the following conditions hold. So okay, the property, but of course, these properties will be generalized for the notion of common infinity categories. But now consider some particular cases, for example, like this. And the last property is about two cell conservativity. So for any natural transformation, you have the following property that if these arrows are isomorphisms, then the two cell tau is isomorphism as well. And the proof is standard here. So consider the quasi-category Q. Quasi-category consisting of functors between infinity category X and infinity category A. And in this setting, we know that the following comparison functor is Smothern. And also consider the following functor between over categories. So we can form the following functor over the category from category consisting of functors between X and A cross A. And this functor will be also Smothern. And from this, easily follows that we have the properties above. So surjectivity on objects corresponds to one cell induction. So fullness of Smothern functor corresponds to two cell induction, and conservativity corresponds to two cell conservativity. So it just follows from the fact that this comparison functor is Smothern. Okay. So, but the functor alpha corresponded to this corresponded to this two cell alpha is not unique. So recall that one cell induction means that for any two cell alpha, you can construct a map alpha, fancy angled map. I don't know how to say angled map, angled alpha. So yeah, you have a the correspondence like this. But this map is not bijective. So this map is not unique. This angled alpha. However, they are unique up to fibered isomorphisms. So the following proposition tells us about the following thing. So whisker with this natural two cell induces a bijection between two cells and the fibered morphisms from X to A2 like this, modulo the fibered isomorphisms. So fibered isomorphisms means that we will say that alpha and beta are equivalent or fibered isomorphic if there is a diagram like this, such that it is commutative. Okay. Yeah. So you have the following correspondence. So the following bijection. So you should take not just alpha, angled alpha, but isomorphic classes of angled alpha, and then you win. So let's prove this proposition. Consider the following Smathern functor. I know that there is such one, and the fibers of this Smathern functor are connected groupoids. So we know by the sum of previous proposition that the fibers are connected groupoids, and it means that the objects of the fiber over, say, these two cells. So these two cells we can take from this category, and the fiber over these two cells are functors which look like this, functor from X to A2, such that the composition, the Whiskeran composition with K equals alpha. And what about morphisms? So the morphisms are invertible two cells that whisker with P1, P0. This natural this natural two cell whisker with this arrow to the identity two cell. So and the action of the Smathern functors defines a bijection between the objects and its and their corresponding fibers. So anyway, it will be clear. It will be more clearly. So later I'll explain in the general statement, and I suppose that it will be more clear than this proof. So what about uniqueness? So arrow infinity categories are unique in some sense. So modular fibered equivalences. Now define fiber equivalences. Fibered equivalence over an infinity category B in some infinity cosmos K is an equivalence over B. So these maps should be isofibrations. in the sliced infinity cosmos K over B. So we will introduce the notion of sliced infinity cosmos later. So to form this category, you should take only isofibrations as objects. So any object of this sliced category looks like this, and so fiber equivalence is just given by this diagram. The following proposition about uniqueness of arrow infinity category. So any isofibration like this, fiber equivalent to P1, P0. For any fiber equivalent, and this can be encoded by 2-cell. And it satisfies the weak equivalence property. So you have an arrow category modular of fiber equivalences. So it's something like that. The next important notion is the comma construction. So in ordinary one categorical set. So recall that if you have a cospan like this in the ordinary set, where ABC are ordinary categories, objects of this comma category are triples, which look like this. So they consist of two objects C and B, and the map H between G of C and F of B, morphism in A, and morphisms of these comma category are pairs S1, S2, such that the following diagram commutes, and the second, the composition looks like this. So you just compose this by coordinates. Okay, and the identity element is just identity on the corresponding objects C and B. So, but equivalently, we can say that we can form the following pullback. So consider the following cospan, and from this we can form a pullback, and objects of this pullback will be CBH. Yeah, you know that in the ordinary setting, you just take Cartesian product of objects of C cross B and this arrow category, and it will be look like this. And what about morphisms? So also on the of course this objects should fit into this diagram, but in this case it means that the map H will be look like this. So H should map G of C to F of B, and it encode the fact that this is object of comma category. So what about morphisms? So in this case we will have the same picture. So you just take such products between morphisms which fit into this diagram. So such that you have a commutativity of this diagram. So morphisms will consist of this S1, S2H, yeah, S1 is just a morphism between S1 is morphism in C in the category C, and S2 in the category B. So and you should have the so commutativity of this diagram translates to the following identification. So J cross F of S1 S2 equals just P0 P1 of the morphism in walking arrow category, but morphism in walking arrow category just this commutative diagram. So it translates, of course, to the following definition, the previous definition. Okay, now define the comma construction in infinity cosmos. So definition, a comma infinity category, consider the following cospan. This is a diagram of infinity categories in an infinity cosmos K. The comma infinity category, we will denote it by this com A FG, and the reason why we will do so, so it's easier because this is just a home object in the infinity category set. But we will talk about it later. And now form the following pullback. And the top horizontal functor represents a two cell, this one. And this two cell is called the comma cone in the homotopy to category K. So of course, the original definition translates to the new one, but of course we should take the definition using pullback notion. So in this case, you can translate it to the infinity categorical set. Yeah, and in this setting, these two cell is the comma cone. So sometimes I will denote this comma category in the following manner, or like this, or sometimes like this. So consider the following example, the following easy example. The infinity category of arrows is a special case of the comma construction. So just consider the identity cospan or span. Then you can form this pullback, and of course this pullback is a trivial one. So this vertical arrow coincides with the first one, and you have that this ID over ID equals A2. So the generic arrow of the infinity category of arrows can be regarded as a comma cone. Okay, generic arrow is a comma cone. Now, pullbacks of isofibrations. So pullbacks have a weak two-dimensional universal property, and this is important to prove that equivalences pull back along isofibrations to equivalences. So in this case, you will have that the category is the right I forgot right not exact, but right. Never mind. Okay. It gives the equivalence invariance of pullbacks in infinity cosmos. Okay, consider the following proposition about the weak universal property of the pullback. So it means that first you have a one cell induction. So a commutative square over the cospan factors uniquely. So it looks like the ordinary definition of pullback. So on the level of one cells, there is not weird. It's okay. And the next level is a two-cell induction. And in this case, you have for given functors x and x prime and natural transformation alpha from qx to qx prime such that the following equality holds. So these compositions, these two cell compositions, or whiskerons are equal. So this one are equal. Then there exists natural transformation tau, such that the following diagram commutes. So q tau, this whiskeron equals alpha, this one, and this whiskeron equals this one. Okay, and two-cell conservativity for any two-cell like this, if both arrows are isomorphisms, then this two-cell is an isomorphism too. So it looks like similarly to the previous proposition, and this pointed proposition means that we should use some sort of smattering property. So consider the pullback diagram of quasi-categories. And we apply the fact that the canonical functor between pullback and H and pullback of H's is Marfaran for any pullback diagram of quasi-categories of the form. So we apply this fact, and in this setting, so here we have just we have just the fact that this map is a smattering function, and from it it's easy to derive these points with these items in the proposition. Okay, the next proposition tells us about that in infinity cosmos, the pullback of an equivalence is an equivalence. So we have a right proper category. Infinity cosmoi are right proper. It means once again that the pullback of an equivalence is an equivalence. Okay, but I'll omit the proof. It is not hard, but it's quite technical, and it's not interesting. suppose. So the following proposition said that pullbacks are an equivalence invariant constructions in any infinity cosmos. So suppose that you have a cospan and you replace it by equivalent cospan. Then in this setting, you will have an equivalence between the pullbacks of these cospans. So this map between pullbacks is again an equivalence. And now prove this. First, we can replace the map. Factorize the map between C and A. So by Ken Brown factorization property or axiom. So as a weak. Sorry, not this one, but this one. We factorize this map from C bar to A bar using Brown factorization lemma as trivial cofibration and isofibration or fibration in this model category. So we have a diagram like this. So P, yeah. So we can form the pullback here, and we get P, and we have an induced map from C to P, and since this is a pullback, then we know that we use the right property to verify that this vertical map from P to P bar is a weak equivalence, and by 2 of 3 we can see that we have these equivalences, and it means that the remaining map is also a weak equivalence. So we, yeah, but and hence we can suppose that these maps are just isofibrations. So we can suppose that these maps are isofibrations. And in this setting, we will have a diagram like this. And also we can suppose that the left-hand side square diagram is a pullback diagram, is a pullback. And in this case, it's easy to verify that the induced purple map is an equivalence. So we can form the following cube diagram. So we can start with the bottom of this cube, and after that we can draw the left-hand side of this diagram. So this is just left-hand side of this diagram, and there is this top side of the cube, top face, and we know that they are pullbacks, and it means that this face is also, this facet is also pullback diagram. But we know that this map from B to B bar is weak equivalence, and by right properness, we can derive that this map is also a weak equivalence. Okay. Now map between commas. So as in the case of okay. So we suppose that we are given a commutative diagram. Then this commutative diagram induces the following map between comma categories. So and also if these vertical maps are trivial fibrations or isofibrations or equivalences, then the induced map is again an isofibration as well. Briefly. Okay. So if you know some information about these arrows, then we have some information about this arrow. So the proof. So consider the following diagram, and this diagram form this pullback, and we have an induced map, the Leibniz tensor map induced by this inclusion. And the easy lemma said that if we have a diagram looks like this in a category of fibrant objects, if R and Z, so Z and R, are both trivial fibrations or just vibrations, then the induced pullback maps, so pullback maps between these square diagrams is again a trivial fibration or vibration respectively. So it can be proven from the consideration of the cube diagram. So I think I can skip it now. Okay, the next proposition is about the weak universal property of the comma infinity category. So we have a comma cone, and this comma cone has a weak universal property in the homotopy 2 category. And as usual, we have the three items. So the first one is about one cell induction. So any diagram of the form, any commutative square of this form, can be factorized in the following manner. So there is an alpha such that you have this identification. So okay, so this is a sort of a generalization of the property of infinity of arrow infinity category, you know. The first point, the first item is about two-cell induction. So given two functor a and prime from X to this comma category, and suppose that you are given natural transformation tau 1 and tau 0. So I mean this. I mean this natural transformation. Suppose that you have this one. Suppose that you have a natural transformation tau 1 and tau 0, such that after after composing with the natural two-cell phi, you will have the equality. In this setting, there exists a natural transformation tau between A and A prime, such that we have the following pictures. So tau fits in the following diagrams. This whiskering gives you the following diagram. So these two cells can be replaced by this one, and also in this case. So they are they're differed by the indices. So here we have a tau 0, p1, and this. In this case, we have a tau 0 and 0. Okay, and the two-cell conservativity for any two-cell, if these arrows are isomorphisms, then tau is so. And this is a routine verification, routine work to prove this proposition by means of the notion of smattering functors. So apply this functor between infinity cosmos k to the category of quasi-categories, and we apply it to the following diagram. So this diagram from the definition of common category, and after that we will have the following diagram, and from this it can be derived that you will have a smattering functor fitting this diagram, and but by definition of by definition of smattering functor, you can derive the previous items. So we are done. So of course it's so the proof is full, but I think that so some details you should verify or reflex or think about separately. So to be comfortable with this stuff. Okay, the functors alpha angled alpha induced by a fixed natural transformation are unique up to fibered isomorphism over C cross B. So as in the case of arrow infinity category. Now the following proposition is about one cell induction is unique up to isomorphism. So it is also some sort of a generalization of the corresponding results about arrow infinity categories, but now we will prove it without pain. It's easy to do it. So recall that you have an bijection with with these two cells, and these these classes of fibered isomorphisms. So fiber isomorphism means that you have the following diagram between one cell alpha and one cell beta. So, in other words, any one cells A and A prime. So A is C and A prime is B, of course. No, sorry. Just a second. Yeah. Okay. For any one cell from X to this comma categories, suppose you have this one. Over weak comma object, this is a weak comma object that are induced by the same comma cone alpha. So suppose that you have this two cell alpha, and you can form the map alpha, and suppose perhaps there is another map alpha prime, or sorry, not alpha, but A and A prime. So this is it should be replaced by A or A prime respectively. So suppose that you have two cell alpha, and if you have two corresponding variants of this arrow, it means that these variants are isomorphic. So there is a diagram like this. Okay, prove it. So the first possible approach is that fibers of Smatherian functors are connected groupoids, and it proves everything. But more elementary and self-contained proof is the following. So you have a two cell alpha, and you can factorize it in the following manner. You have a two ways to do this. So this equivalent ways. And also we know that from this equality, from this equality, we know that P0 alpha here, P0 alpha equals P0 alpha prime. So it equals B, and P1A equals P1A prime, and it equals C, and also Phi A, this Whiskeran and this Whiskeran are equal, and from the first pair of these equalities, you will have the following identity two cells. So you know that these composites are equal. So of course you have here an identity morphism two cell, an identity two cell, and in this case, this case is similar. And this the last equality transforms to the following equality of diagrams. So you know that you can form these giant diagrams, but you know that the top squares are identities, and it means that you can just drop it, and it is equivalent to the following diagram, but and here is the same, but they are equal by this equality. Just this Whiskeran are equal. Okay, So by the two-cell induction, there is a tau such that the following diagrams commute. The first one and the second. And from this two-cell induction, we will have that P0 tau is an identity and P1 tau is an identity too. And it means by two-cell conservativity that these arrows are isomorphisms, and hence tau is isomorphism too. So it means that if you have some alpha, alpha, and you recovered some A from X to the comma category and A prime, then they are equivalent. They are isomorphic by some two-cell tau. Okay. As in the case of arrow categories, if you are given the following diagram, then you have a induced map between comma infinity categories. So you have the following induced map between comma category FG and comma category F bar G bar, such that the following diagrams are equivalent. So recall that phi is a canonical two-cell, and you will have the following picture. So this is some sort of observation, and I won't give the proof. Now, the notion of infinity of comma infinity category motivates the mapping space, the notion of mapping space in infinity cosmos setting. So the mapping space between two elements, X and Y, of an infinity category is just the following comma infinity category from X to Y. So this is a pullback. Okay. So let's discuss some properties. First of all, mapping spaces are discrete. It means that for any pair of elements X and Y of infinity category A, say, the mapping space for the mapping space from A X Y, the following is true. So the quasi category of functors between X and this home is a Kan complex. Kan complex. So prove this. We must show that this homotopy category is a group poet for any infinity category. You know that the notion of group poet in simplicial setting is equivalent to the notion of Kan complex. So in the setting of quasi categories, and of course this is not trivial theorem, but there are a lot of ways to prove it. And okay, so we should prove that this two-cell is invertible. But it is if this whiskering is an invertible two cell. So we can consider the following whiskering. It is just about the fact that it is just about the two cell conservativity. So this whiskering is an invertible to cell by two cell conservativity. It is so it is so as we have a map to the two-terminal object. So the map to terminal objects in this case so yeah, we will prove the theorem if we prove that this composition is an invertible two cell. Yeah, but by two cell conservativity. So you know that if we know that these guys are isomorphisms, then two cell here is an isomorphism too. And but this condition is equivalent to say that this whiskering gives an invertible two cell, but it is so as the map so we have a map to the two-terminal object. Okay. The next proposition is about uniqueness of comma infinity categories. So for any isofibration from E to C cross B, that is a fiber equivalent to this usual comma category, comma infinity category. Then the two cell encoded by the isomorphism between E and this guy satisfy the weak universal property of the comma infinity category. So briefly, if you have an isomorphism between E and home at G, then this original isofibration should be fit into weak universal stuff. Okay, and vice versa. If you have the map D1, D0 from D to C cross B, and the isofibration between E and C cross B, and also you have these diagrams satisfying the weak universal property, then D and E are equivalent under the C cross B. So prove this uniqueness property. First of all, construct this direction is standard one. We should construct a smattering factor, and we are done. For the other direction, know that suppose that you have this decomposition. You know that you have an universal property, then you have the decomposition like this, and also you have the decomposition like this. So, and now we will play the game, the following game. So we consider the following composite epsilon angled delta angled epsilon, and so just firstly you apply angled epsilon. After that you apply delta angled delta, and then epsilon. So you have a factorization from E to through E. So but we know that this factorization is unique up to isomorphism, fiber isomorphism, and then you should have this isomorphism. But at first I skipped it, but this is of course holds by trivial reasons. So just consider the composition epsilon and delta. So where epsilon here, epsilon delta, yeah, and then you get delta, usual delta, and then you should compose it with the epsilon and angled epsilon, yeah, and you will have epsilon, of course. And in the same manner, you can verify that this equality holds by trivial reasons. So, but these equalities give us another way to decompose decompose E through E, E through this canonical natural to cell, and it means that this composite will be equivalent to identity on E over C over C cross B. And in the same manner, you will have the following isomorphism. Thus we have proved that epsilon and delta are equivalent. So now we have a uniqueness property of comma infinity categories. Okay, thank you for listening.
Yeah, thank you for this great talk, and for the accompanying cats.